Bernoulli Theorem. Aim of the experiment: to verify the Bernoulli's theorem. Bernoulli's theorem states that for a continuous, steady, and frictionless flow, the total head, that is the sum of the pressure head, velocity head, and the elevation head at any section remains constant.
The head form of the Bernoulli equation is obtained by dividing the energy form throughout by the magnitude of the acceleration due to gravity g, so that each term has dimensions of energy per unit mass of fluid. Bernoulli theorem states that during steady flow, the energy at any point in a conduct is the sum of the pressure head P, velocity head V, and elevation head Z. Pressure head or static head. The pressure head represents the flow energy of a column of fluid whose weight is equivalent to the pressure of the fluid. Kinetic head or velocity head. The kinetic head represents the kinetic energy of the fluid. It is the height in feet that a flowing fluid would rise in a column if all of its kinetic energy were converted to potential energy. Elevation head or gravitational head. The elevation head represents the potential energy of a fluid due to its elevation above a reference level. The sum of the kinetic head, pressure head, and elevation head of a fluid is called the total head. Thus, the Bernoulli's equation states that the total head of the fluid is constant. That is, energy is equal to velocity head plus pressure head plus elevation head is equal to constant.
The following assumptions must be met for the Bernoulli equation to apply. The flow must be steady, that is, the flow parameters, velocity, density, etc., at any point cannot change with time. Second, the flow must be incompressible. Even though the pressure varies, density must remain constant along a streamline. Third, friction by viscous forces must be negligible. The above equation has been derived by assuming that the velocity at every element of a liquid across any section of the pipe is uniform, practically which is not true. The elements of the liquid in the innermost layer have the maximum velocity. The velocity of the liquid decreases towards the walls of the pipe. Therefore, we must take into account the mean velocity of the liquid. Second, in deriving the Bernoulli's equation, the viscous drag of the liquid has not been taken into consideration. The viscous drag comes into the play when the liquid is in motion. Bernoulli's equation has been derived on the assumption that there appears no loss in energy when a liquid is in motion, whereas some kinetic energy is converted into heat energy and part of it lost during the shear force. 4. If the liquid is flowing along a curved path, the energy due to centrifugal force should also be taken into consideration.
Applications of Bernoulli's theorem are in venturimeter, in orifice meter, and pilot tube. Venturimeter. Venturimeter is an apparatus used to find discharge of liquid flowing at any point along pipeline when it is running full. Main parts of venturimeter are covering part. It is the part of the venturimeter where the fluid converges. Second, throat. It is the portion that lies in between the converging and diverging part of venturi. In the throat portion, the cross-section is much less than converging and diverging portion. When the reaches the throat, its velocity increases and pressure decreases. Third, diverging part. It is the part of the venturimeter where the fluid get diverges and the cross-section area increases. Orifice meter. It is used to measure discharge in pipe. An orifice meter consists of a plate having sharp edge, circular hole known as orifice. Hg manometer is used to find the pressure difference between pipe and orifice. Pilot tube. It is used to determine the velocity of flow of a pipe or stream. Pilot tube consists of a glass tube bent in shape of C and inserted. The liquid rises up in the tube due to pressure exerted by the flowing liquid. By measuring the flow due to liquid in tube, velocity of liquid flow can be found out.
The equipment is designed and fabricated to demonstrate the Bernoulli's theorem. It consists of a test section made of acrylic. It has convergent and divergent sections. Pressure tapings are provided at different locations in convergent and divergent sections. Present setup is self-contained water recirculating unit provided with a sump tank, centrifugal pump, etc. An arrangement is done to conduct the experiment on different flow rates. Flow rate of water is measured with the help of measuring tank and stopwatch.
Now I'm going to tell you how we are going to perform this experiment. Firstly, open the inlet valve slowly and allow the water to flow from the supply tank. Now adjust the flow to get a constant head in the supply tank to make flow in and out flow equal. Under this condition, the pressure head will become constant in the piezometer tube. Note down the quantity of water collected in the measuring tank for a given interval of time. Now compute the area of cross section under the piezometer tube. Compute the area of cross section under the tube. Change the inlet and outlet supply. Note the reading. Take at least 3 readings as described in the error.
The observation table. For 100%, at different location we see different piezometric readings. So as we move from location 1 to location 14, we see that piezometric reading first decreases until the middle and then it increases till the end. Similar pattern is followed for 75%. The piezometric reading first decreases until the middle and then starts to increase. The graph. On y-axis we have plotted head per meter. On x-axis we have plotted head against distance from inlet, which is distance per millimeter. The red line is representing total head, the blue line is representing static head, and the green line is representing dynamic head. So if we talk about total head, the red line, we see that as we increase the head against distance from inlet, the head per meter decreases. But in the case of static head, it is different. So for static head, we see that as we increase the distance per millimeter to some point, head per meter decreases. But after that point, the head per meter starts to increase with increase in head against distance from inlet. For dynamic head, we observe that from the beginning, this head per meter increases with increase in distance per millimeter until some point, and then head per meter decreases with increase in head against distance from inlet.
Precautions: carefully keep some level of fluid in inlet and outlet supply tanks, and when fluid is flowing there is fluctuation in height of piezometer. Note the mean position carefully. Sources of error: the Bernoulli apparatus should be in level. Possible leaks in constant head inlet tanks. Debris in the Bernoulli's channel and manometer tap inlet. Thank you.